Okay, everyone, this problem asks us to do the electron configurations of some atoms and some ions. And so in order to do electron configurations, the thing that I would suggest that you start with is this mnemonic that I'm drawing in the bottom right. If you set up this mnemonic in this way, it's sort of a increasing set of orbitals. So starting with 1s, and then you get 2s, then we can add a p, so the 2p level, then 3s and 3p. Now we can add d, do the same thing at the 4 level, we can add an f, do the same thing at the 5 level, we can add a g. And then when we start using the diagonals, then we can see what order the orbitals come in terms of energy. And that way we know how to fill them, because they're going to fill in order of energy, lowest to highest. So we draw these arrows on the diagonal to tell us what orbitals come in. And so 4d, 5p, but then I need another orbital that I don't have written down to complete this diagonal. I would need the 6s. Okay, and so this is what I'll use to do these electron configurations. And then I just need to remember that I can put 2 electrons in a set of s orbitals. There's only one. I can put 6 electrons in a set of p orbitals because there's 3. And I can put 10 electrons in a set of d orbitals because there's 5 of them. So carbon has an electron configuration of 1s2, 2s2, 2p6. There's 6 electrons for carbon. Now, phosphorus has 15 electrons, so it would be 1s2, 2s2, 2p6, and that gets me to then 3s2, 3p3. That gets me to 15. All right, and then let's move on to magnesium. Magnesium has 12 electrons, so 1s2, 2s2, 2p6, that's 10, and 3s2, that's 12. All right, now what do we got? Let's do O2 minus. Now this is an ion. Oxygen has a total of 12 electrons from the periodic table, but it has a total of 8 electrons from the periodic table, but because it has a negative charge, it gains 2 electrons. So it went from 8 to 10 electrons. So that would be 1s2, 2s2, 2p6. That's 10 electrons. Okay, so now we're going to get into a transition metal. This transition metals can give us problems. And the reasons transition metals can give us problems is because of the energy spacing of the orbitals actually gets closer together. And this mnemonic down at the bottom right doesn't actually work 100% of the time. Now, some of these are going to be a little bit easier to figure out. Regular old iron has 26 electrons. And so we would write it like this, 3d6. But it's going to be iron 3 plus, and so I need to remove 3 electrons. Well, where do they come from? Well, in this case, it turns out that the 4s orbital is actually higher energy than the 3d orbital, particularly if you start making positive ions with it. So the energy differences between 4s and 3d are very close together, and they don't actually follow the mnemonic order. And so there are some exceptions, and you kind of have to be familiar with these exceptions. So in the transition metals, you're typically going to be removing the electrons from the highest principal quantum level first. And so 4s, 4 being higher than 3d, 4 versus 3, we're going to start with 4. And then we're going to have to remove 3 total. So they've got 2 in the 4s. I've got 6. I'll have to remove that third one from the d orbital. So I end up with 3d5 as the final electron configuration. Okay, the sodium ion is pretty straightforward. It has also 10 electrons. So it's 1s2, 2s2, 2p6, 11 electrons in neutral sodium. It lost 1 because it's a positive ion. So it's 2p6. All right, so copper has 29 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, I'm up to 20, 3d9. That would get me 29. Now, there's going to be an exception to this one as well. It turns out that the 3D orbitals are lower energy than the 4s orbitals, even though our mnemonic doesn't seem to indicate that. So it's just an exception that we have to memorize. And so the way that I would actually write it would be 3D10 and then 4s1. That's how you'll see it, certainly in Wikipedia or in your internet searches. So let's go ahead. Oh, that was supposed to be ruthenium 3+. And so let's kind of get some room there. And let's add up the electrons. There's 44 electrons in ruthenium. So ruthenium 3+ has 41 electrons. So that would be then 1s2, 2s2, 2p6, that's 10. 3s2, 3p6, 4s2, that's another 10. So we're up to 20. 3d10, that's 30. 4p6, that's 36. And then another, let me move that over, 5s2 and 4d6. So that would be 44, but we need to remove 3 electrons. Again, I'm going to remove them from the 5s orbital first. So I end up with 4d5 as the final electron configuration for ruthenium 3+. Again, removed them from 5s first, and then another one from 4d to get the 4d5 electron configuration. Okay, that's my final answer. Thanks, guys.